this homework question, this is like the question we did in theory with symbols in class. We have a conducting bar, the length is 3 centimeters. It's on conducting rails, so this forms a closed circuit. The entire resistance is 0.05 amps, 0.05 ohms, sorry, and it's set in a magnetic field of 0.626 teslas, and the direction is shown with these x's, it's into the page. The bar is being pulled to the right with a constant speed of 42 centimeters per second, or 0.42 meters per second. Find/show the direction of the induced magnetic field, induced current, and induced magnetic force. And this means the induced magnetic force on this sliding bar right here. Okay, so what happens in our problem is our bar is moving to the right. As it moves to the right, we're increasing the magnetic flux. Remember, flux is magnetic field times area. As we move our bar this way, we see we get an area of more x's into the page. Okay, so we're creating an area where there's more magnetic field pointing into the page. So the direction of the induced magnetic field will oppose that increase into the page, and it will create field out of the page. So the induced magnetic field will be out of the page. Now for the direction of the induced current, we're going to use our right-hand rule that says our thumb is our current and our curled fingers are our magnetic field. We're going to think about the current in this part of the bar, and we know that the magnetic field right here is out of the page. So for our right-hand rule, we're going to match our fingers to this magnetic field. We're going to point those towards the ceiling. Look at what our stuck-out thumb is doing. It's moving upwards. So the direction of the induced current is straight up in the bar. So if the induced current moves up in the bar, it comes up here, comes around this way and down, this way and over, back up into the bar. Overall, this is a counterclockwise direction. Find the direction of the induced magnetic force. There's an induced magnetic force because now we have a current carrying wire in a magnetic field which points into the page. Using our right-hand rule, we know that F is IL cross B. I and L are in the same direction, so we put our thumb in the direction of the first one, I or L. Then we have to extend this finger and make it match the x's here. So I've got to twist my hand until it points into the page. Next I have to extend my middle finger, and that's going to show me the direction of the force. My middle finger is pointing to the left, so the direction of the magnetic force on this bar is to the left. We'll draw that in the picture. We'll label that FB. And that's our induced magnetic force. So that's to the left, and we know that from the right-hand rule. So our induced magnetic field we figured out because of Lenz's law. Our induced current we figured out from our right-hand rule relating current and magnetic field. Our induced magnetic force we found from our right-hand rule that F equals IL cross B. Okay, those are all of our directions. We've got those sorted out. Next we want to find the magnitudes. What's the induced potential? What's the induced current? And what's the induced force? To find the induced potential, we're going to use Faraday's law. Faraday's law says that the magnitude of the induced potential is equal to the magnitude of the change in flux, magnetic flux. So our next step is we'll fill in that magnetic flux is B times A times cosine theta. Our area vector is either into the page or out of the page. Our magnetic field is into the page. Those two vectors are parallel, so theta equals 0 degrees, and cosine of 0 is 1. Okay, so we've got d by dt times BA. B is a constant, so that can come out front. D by dt of the area. The area means the area where our magnetic field is. That's going to be the length of the wire times the width. Length is a constant value, so that comes out front next to our B. And we've got dw by dt. dw by dt is how fast this width is changing. That's going to be in meters per second. This is the velocity of the sliding bar. So the magnitude of our induced potential is the magnitude of B times the length times the speed. So that's going to give us 0.626 teslas times our length, 0.03 meters, times our speed, 0.420 meters per second, gives us an induced potential of 7.89 times 10 to the minus 3 volts. Okay, what's the magnitude of the induced current? Here we'll use Ohm's law. We know that V equals IR. So the induced potential is the induced current times the resistance. The induced current is the induced potential divided by the resistance. We're given that our resistance is 0.05 ohms. That gives us an induced current of 0.158 amps or 158 milliamps. So up here we found induced potential. This only exists because the bar was moving. This is our induced current. This only exists because the bar is moving. If the bar stopped, all of these things would go to zero. And last, our induced force. We know that magnetic force has a magnitude of I, the current, times the length, times the magnetic field, times sine of theta, but everything is perpendicular, so theta is 90 and sine of 90 is 1. Okay, so our current is 0.158 amps. Our length is 0.03 meters. Our magnetic field is the magnetic field in which this bar is sitting. That's our 0.626 Teslas. That gives us an induced magnetic force of 2.96 times 10 to the minus 3 newtons. Might notice here that part B asked for the magnitude of the force. So we just had to give a number here. If it had asked for the induced force, we would have to give the number with the direction, which is to the left. Okay, part C, find the magnitude of the pulling force. So if our bar is moving to the right, something must be pulling it to the right. So somebody has their hands on this bar, or it's hooked up to a machine, and it's being pulled to the right. It wouldn't move to the right if there were no force pulling it. So let's see about the magnitude of that pulling force. What we know in our problem is that it's moving with constant speed and constant velocity. If our velocity is constant, it means our acceleration equals 0. So let's write Newton's second law. Sum of the forces is mass times acceleration. The net force is the magnetic force to the left, so we've got minus FB. We've got our pulling force to the right, plus F pull equals mass times 0 equals 0. So the magnitude of our pulling force is equal to the magnitude of our magnetic force, which we said was 2.96 millinewtons. Here again, part C asks for the magnitude of that pulling force. If it asked for the force vector, we would say 2.96 times 10 to the minus 3 to the right.